In our previous video, we went over Hess's law and Born energy to find the enthalpy change of a chemical reaction. So in this video, we're gonna go over standard enthalpies of formation. So this is also like another method to find the enthalpy change of a chemical reaction. So standard molar enthalpy of formation is the change of enthalpy, like how much energy is like gained or like released when 1 mole of a compound is formed directly from its element. So we need to write the chemical reaction for the formation of the following compound. So let's begin with A. So the only elements we see in ammonia is just nitrogen and hydrogen. The reason why I put a 2 there is because nitrogen and hydrogen are diatomic. They can't exist on its own. So this gives 1 mole of ammonia. And now we just balance at this point. So on the right side, we have 1 mole of nitrogen, and on the left side, we have 2 moles. So we have to balance it. So we'll put a 1/2 as the coefficient. And on the right side, we have 3 hydrogen, and on the other side, we have 2 hydrogen. So I'll put 3/2 as the coefficient. And if you don't know why I put it, you can just solve for it like this. So 2x equals 3. I'll divide both sides by 2, and x equals 3/2, which is just 1.5. So now our reactions are balanced. So this is the reaction if you want to form exactly 1 mole of ammonia. Now for hydrogen chloride, the only elements we see are hydrogen and chlorine. So this gives exactly 1 mole of hydrogen chloride. So on the right side, there's 1 hydrogen, and on the left side, there's 2 hydrogens. So we'll put coefficient as 1/2. And now for chlorine, there's 2 here, and there's 1 here. So I'm going to balance it by putting 1/2 here. And now this is the reaction if you want to make exactly 1 mole of hydrogen chloride. Now let's do C. So the only elements we see are potassium, and we gotta be careful here. This is also a compound, sulfate. So there's sulfur here, and then there's also oxygen here. These are the only elements we see. So potassium plus sulfur plus oxygen, this gives 1 mole of potassium sulfate. So now we just balance here. So on the left side, there's 1 potassium, and on the other side, there's 2 potassium. So we're going to put 2 as a coefficient. And now let's focus on sulfur. So on the right side, there's 1 here, and on the left side, there's 1. So we don't really need to do anything here because it's already balanced. Now for oxygen, there's 2 oxygen here, and there's 4 here. So we'll multiply by 2, the coefficient. So this is the reaction if you want to exactly make 1 mole of potassium sulfate. Let's do the last one. So magnesium hydroxide. So there's magnesium, and there's oxygen, and there's hydrogen. These are the 3 elements we see. So magnesium plus oxygen gas plus hydrogen. This gives magnesium hydroxide. So let's just balance. So on the right side, there's 1 magnesium here, and there's also 1 magnesium on the other side. So this is already balanced. And now for oxygen, there's 1 oxygen here. I meant there's 2 oxygen, but like there's 1 mole of it, And for hydrogen, there's 2 on this side, and there's also 2 on the other side. So this is already balanced. And that's the chemical reaction if you want to make exactly 1 mole of magnesium hydroxide. And here are more things you need to know about enthalpies of formation. So the examples that we just did were all like an example of standard formation equations. And here are some examples that are not standard formation equation. So let's say you have magnesium oxide reacting with water, giving you magnesium hydroxide. This is not a standard formation equation because these are all like compounds you see. We only want elements. Number 2, what is the molar enthalpy of combustion of methane? So here we're given the balanced reaction of methane, and we're also given the standard molar enthalpy of methane, water, and carbon dioxide. Now we need to find the enthalpy change of the reaction. So there's exactly 1 mole of methane, so we can just use this number here. So this one here is going to be negative 74.4 kilojoule, and there's only 1 mole there. And now for oxygen, it's a bit special. So you need to know that the standard enthalpy of formation is 0 whenever you have elements that are in their like standard state. It's like normal state. Like for example, like oxygen is usually in its gas phase, right? So when you have that, the standard enthalpies of formation is 0. But if it's in a different state like liquid, then yeah, it's not 0. Remember, it applies to every other element, not just oxygen. So let's say we have potassium and it's in a solid state. So when you have that in the solid state, it's its normal state, that means the standard enthalpy of formation is going to be 0. But however, when you have potassium in its liquid form, the standard enthalpy of formation is actually not 0, it's actually 2.3 kilojoule. We're gonna put 0 kilojoule here. Now for water, it's negative 285.8 kilojoule per mole, and there's 2 mole of water in this reaction, so the unit mole cancels. That gives negative 571.6 kilojoule. For carbon dioxide, there's only 1 mole, so for carbon dioxide it's negative 393.5 kilojoule. And to calculate the enthalpy change of the reaction, so H of RxN, which is a reaction, it's simply the standard enthalpy of formation of the product minus the standard enthalpy formation of the reactants. So this is the reactant and this is the product. So the enthalpy change. So on the product side, we have negative 571.6 kilojoule plus negative 393.5 kilojoule. This is only for product, you see. This is for water and this is for carbon dioxide. Minus. So on the reactant side, we only have the standard enthalpy formation of methane, which is 74, so negative 74.4 kilojoule. So this and this becomes positive because negative times negative is positive. So now we simply add them up. This gives negative 890.7 kilojoule. Therefore, the enthalpy change of this combustion of methane is negative 890.7 kilojoule and per mole. Number 3. Consider the reaction below. A. What is the enthalpy of a reaction? B. What amount of heat would be released when 1 kilogram of iron is produced? So let's begin with A. So for ferric oxide, there's 3 mole of ferric oxide. So 3 mole times, and we are given the standard enthalpies of formation for ferric oxide, which is this one, and that's negative 1118. Guys, by the way, I made a mistake here. It's meant to be 1118.4. So kilojoule per mole. The standard enthalpy of formation of aluminum is 0 kilojoule because aluminum is a element and this is in a standard state. Aluminum is solid. And now I'll begin with this one. So this one is also 0 kilojoule because iron is an element and its normal state is like solid at room temperature. And for this, the standard enthalpy of formation is negative 1675.7 kilojoule per mole, and there's 4 mole of aluminum oxide. So the mole cancels, and here the mole cancels. Now we simply just multiply them. That's negative 3355.2 kilojoule, and that's, by the way, that's the reactant side. And here, so that gives negative 6702.8 kilojoule, and that's the product side. Remember, this belongs to the product side and this belongs to the reactant side. So the enthalpy change is equal to the standard molar enthalpy of the product minus the standard enthalpy of formation of the reactant side. So the enthalpy change is equal to, this is the product, so negative 6702.8 kilojoule minus, I don't know why my minus sign doesn't look good, 3005 kilojoule. So this gives, so that gives negative 3347.6 kilojoule. So this is the enthalpy change of the reaction. Now, what amount of heat would be released when 1 kilogram of iron is produced? So for this one, we need to first find the molar enthalpy. So the molar enthalpy is equal to the enthalpy change of this reaction over the mole. So the molar enthalpy is equal to negative 3347.6 kilojoule over and there's 9 mole of iron, as you could see here. So that gives negative 371.956 kilojoule per mole. So that's the molar enthalpy of iron. And what we're trying to find is the enthalpy change of iron. So let me just put Fe instead of reaction. So we're trying to find that. The enthalpy change is mole times the molar enthalpy. We already have the molar enthalpy here, so we just multiply by the number of moles. And how do we know how much mole of iron we have? We know that mole is equal to mass times molar mass. We know that the mass of iron is 1000 grams and the molar mass of iron is 55.85 grams per mole. So the unit grams cancels and the unit mole cancels, leaving us just kilojoule, which is the unit of energy. That gives negative 6,659.76 kilojoules. And that's the enthalpy change from iron, like that amount of heat released by 1 kilogram of iron. Number 4. Consider the combustion reaction of propane. A. Determine the molar enthalpy of the reaction. B. Find the change in temperature if 3.2 grams of propane burns to heat 4 kilogram of water. So we're also given the reaction and the standard molar enthalpies of formation of the following compound. And before we begin anything, we need to balance the reaction. So on the reactant side, we have 3 carbon, and on the product side, we only have 1 carbon, so we'll put a 3 here to balance that carbon. And now let's move towards hydrogen. So there's 8 hydrogen on the reactant side and there's 2 on the product side, so we'll put a 4 here, so that balances that. Now we need to worry about oxygen. So there's 2 oxygen on the reactant side, and now for the product there's already 6 because 3 times 2 is 6, and there's also 4, so 4 plus 6, so there's 10 oxygen on the product side, so we'll put a 5 here, so because that balances. 5 times 2, that equals 10, so there's 10 oxygen. Great, now our reaction is balanced. Now to find the enthalpy change, it's simply just going to be the standard enthalpies of formation of the product minus the standard enthalpy formation of the reactant. So the enthalpy change, that's going to be, we have 4 mole of water times the molar enthalpy of water, which is negative 285.8. There's 3 mole of carbon dioxide times the standard enthalpy formation of carbon dioxide, which is negative 393.5, and this is only the product side, minus the reactant side. So we know oxygen, there's 5 moles of oxygen, and then times 0 because it's in its gas form. So like the standard enthalpies of formation is always 0 for elements at its normal state, times the standard enthalpies of formation of propane, which is negative 104.7. So the enthalpy change of this reaction, the combustion reaction, so this side here on a calculator, if you add them up, I get negative 2323.7 minus now this one. So 5 times 0 is just 0, and this one here, the minus sign, and here the minus and minus makes a positive, so plus 104.7. So the enthalpy change of the reaction is negative 2219 kilojoule. So that's the enthalpy change of this reaction. And this makes sense because combustion reaction are exothermic reaction, so you're supposed to be getting negative numbers, and if you don't get a negative number, then you need to check your work. Now I need to find the change in temperature if 3.2 grams of propane burns to heat 4 kilogram of water. And to do that, we need to use the concept of calorimetry. And we know that this combustion reaction here is a exothermic reaction, so we can use this formula. The heat lost by propane is equal to heat gained by water. So we need to find how much heat was lost by propane. So the enthalpy change of 3.2 grams of propane will just be the molar enthalpy times mole. So we know that the molar enthalpy is going to be negative 2219 kilojoule, and in the reaction there's only one propane, so 1 mole times, so we know that mole is equal to mass over molar mass. So the mass of the propane is 3.2 grams. That looked horrible. Grams over, so the molar mass of propane, there's 3 carbons, so 3 times, and the molar mass of carbon is 12.01 plus 8 hydrogen, so and the molar mass of hydrogen is 1.008, and they're all in grams per mole. So we can do a little canceling here. The unit mole cancels with this, and the unit grams cancels out. And if you multiply this whole thing, we get negative 161.038 kilojoule. So that is the amount of heat lost by 3.2 grams of propane. Now I'm just gonna convert this into joules. So I'll simply multiply by 1000, and I get negative 161,038 joules. Now I'll get rid of this for more space. So I know that Q is equal to mc delta T. Now we're solving for T, so we're gonna isolate for T. So we'll divide by M and C. Divide by M and C. So this cancels, leaving us just delta T is equal to Q over MC. Now at this point we just substitute. So delta T is equal to, so this time we're gonna have actually positive 161,038 joule. And the reason why is because this number tells us that that was the amount of heat was lost by 3.2 grams of propane. But however, the water gains that amount of energy. So it's positive because the water gains it. You need to be careful. We know that the mass is, so we need to convert into grams because we use grams for the formula. So 4 times 1000 is just 4000 grams. So that's what 4 kilogram is. So 4000 grams times the heat capacity of water, which is 4.18 joules per grams times Celsius. And make sure that your Q is in joules, not kilojoule, or that will mess up your answer by 1000. So the unit grams and grams cancels, the joules and joules cancel, leaving us just Celsius. So T is equal to 9.63 Celsius. Therefore, the temperature change is 9.63 degrees Celsius if 3.2 grams of propane burns to heat 4 kilograms of water. Number 5. The molar enthalpy of combustion for heptane in a bomb calorimeter is negative 4816.7 kilojoule per mole. Determine the molar enthalpy of formation of heptane. So we already have a balanced reaction, and now we know that enthalpy change of the reaction is equal to the standard enthalpy formation of the product minus the reactant. And we're already given the enthalpy change of the combustion of heptane, which is negative 4816.7 kilojoule per mole, but there's only 1 mole of heptane in this reaction, so we're not going to need that, which equals the product. So on the product side, we have 7 carbon, so 7 mole of carbon times, and we know that the standard enthalpies of formation of carbon dioxide is negative 393.5 kilojoule plus this 8 mole of water times the standard enthalpies of formation for water is negative 285.8 kilojoule. Now for reactant, we don't know what that is, so we'll call it X. We're solving for X. So the unit mole cancels out. So the standard enthalpies of formation for the product part is negative. Now I'm gonna make things nicer and multiply everything by negative 1, so it just kind of gets rid of that negative sign. So 4816 kilojoule equals 5040.9 kilojoule plus X. Now I'm gonna simply take this to the other side by subtracting it. So X equals 4816 kilojoule minus 5040.9 kilojoule. So therefore X equals negative 224.2 kilojoule. And I made a little mistake here. So here there's supposed to be a 0.7, which I forgot. I just put it as 4816, but there's supposed to be a 0.7 here. But this is the correct answer though. And that's it for this video. Thank you so much for watching, and don't forget to subscribe.